The Algebra 2 students, we are going to start Chapter 1 today. So today is your very first lesson, and we're going to actually skip Section 1.1. Not going to worry too much about that, and we're going to get into the next two sections, and the reason we're doing that is because it's a lot of Algebra 1 review, and I think you'll be okay. So hopefully it's not that big of a deal. So objective number 1 is we're going to try to identify real number subsets and their subsets, which that's Section 1.2. And then Section 1.3, we're going to take a look at quickly, and that is to simplify and evaluate algebraic expressions. And you've done that. We'll talk about it. I'll show you some examples. Hopefully it should not be any real big deal at all. So if we take a look, the first set of numbers that we're going to talk about are the natural numbers. And those numbers are, basically those are your counting numbers, is what that is. And so if we take a look at the counting numbers, what I mean by that is if you think about how would you go through and how would you start counting, you don't start counting at 0, you start counting at 1, 2, 3, 4, and so on and so on and so on, all the way forever and ever. It's a never-ending set. But the counting numbers are your 1, 2, 3, 4, 5, and on. Okay. So as we take a look at if we talk about like a Venn diagram of the real numbers and their subsets, the smallest set of numbers we're going to talk about is the natural numbers. Okay. So then, if we go back, the next set of numbers we're going to talk about are your whole numbers. And those numbers are the natural numbers, okay? So these counting numbers like we just talked about, and the only difference is we're going to add in the number 0, okay? So in this case, whole numbers start at 0, and then 1, 2, 3, 4, and so on and so on and so on, okay? So again, if we then go to our Venn diagram, at that point, if we go through, let me get rid of that. If we go through and we take our Venn diagram, now I can add the whole numbers just a little bit bigger than the natural numbers. It includes all of these numbers plus one more, so it's a little bit bigger set. Okay. If we keep going, the next set of numbers we're going to talk about are the integers. And the integers are those whole numbers and their opposites. So not only are we including 1, 2, 3, 4, we're also now including the negatives. So -1, -2, -3, -4. Those are your integers. And let me put that down. So now we're talking about, we're coming from our negatives here. And then we'd have like -3, -2, -1. We still include 0, but then we also go 1, 2, 3, and so on. Okay, so those go in both directions. Now we just have added negatives to the mix. Okay, so if we go to the next part and we pull out this next portion, now that means I can add the integers. Those are the next set of numbers that we have. They're a little bit, they include all of these numbers, plus we've got all the negative ones now, the negative whole numbers. So that's our next set. If we keep going, next set of numbers are our rational numbers. And the reason we need to know all these different numbers and what they are, by the way, is just a quick side note, is because as we move forward, we're going to be talking about rational numbers in the future. We're going to be talking about whole numbers, integers, all those kind of things. So you need to know what they are so that you can understand mainly the language and mainly the vocabulary that goes with it. So a rational number is any number that can be made into a fraction, and that includes repeating decimals. So for example, for fractions, if we are dealing with fractions and I said 1/5, that's an example of a rational number because it already is a fraction. But then I could also add to that like the number 4. Why is 4 a rational number? Because you can turn that into a fraction by making it 4/1. We could go through and we could talk about 0.25 would be a rational number. Why? Because 0.25 has an ending, and if it has an ending, that means that we can turn it into a fraction. 0.25 is 25/100ths, or 1/4. Okay, so you can turn that number into a fraction, so it's rational. 0 is a rational number because you can, just like the number 4, you can put 0 over 1. And then if we keep going, one last one, if let's say I would take 0.3 repeating, 0.3 repeating can be written as 1/3. And therefore, that's why that's also in the rational numbers. So rational numbers are any number that can be made into a fraction, including ones that already are. So if we keep going, we've got 2 sets left. Let me go back to the other slide here. And if now we pull in the next part, so now we can put in the rational numbers, and that includes everything inside that we've already talked about. Those are already there, so we can talk about that. Now, we go back to our irrational numbers. And basically, it's the exact opposite, kind of like you'd expect. So any number that you can't make into a fraction are irrational. And there's 2 main types, okay? So they're never-ending numbers is what they are. Meaning, so like this decimal up here, 0.25, we could turn that into a fraction because it ended. It had a place value. Now, repeating decimals work because you can make them into a fraction. But there's 2 types of numbers. First one is the number pi. That would be an example of an irrational number because pi goes on forever and ever and ever and therefore cannot be turned into a fraction. Okay, so you might think pi is 3.14, but remember that's just an approximation. That's a rounded approximation of pi. It's not actually what pi equals. So that's one example, and the other example are square roots. So for example, if I did the square root of 5 and I type that into a calculator, the square root of 5 actually turns out to be approximately 2.23606, and it keeps going and going and going, and that would never end. Okay, so that one would end up being an irrational number. Those are the 2 main ones that we talk about, is pi and square roots. Okay, now square root of 4, that's 2, for example, so that still is up here in the rational numbers and some of these other sets. So now if we go back to our chart here, the last thing that we can add on is if we take all of our set of numbers. I'll move all of these over here just for a second. And there's our set of numbers right there. The reason that I have real numbers sitting at the top is because these are all subsets of real numbers. Basically, real numbers are numbers that you can put on a number line. Anything that you can put on a number line. So that's whole numbers, that's natural numbers, those are integers, you've got negatives, you've got fractions in between the whole numbers, you've got irrational numbers in between those that are, like I said, 2.2356, whatever. Those are all on the number line. And the real numbers then are your numbers that basically we said can be thought of as all numbers at this point. Okay? So that should give you some idea of what's going on with the different sets of numbers. You need to know these sets so that when we talk about them, you can understand what numbers are which types. Okay? That's the diagram of how everything fits in, as we've talked about. And then there's just a few properties of real numbers that I just want to run through real quickly. You don't need to memorize these at all. I just wanted to make you aware of them. They're just the properties that allow us things that we can do. The commutative property just says that we can either add or multiply things in either order. 2 plus 3 is the same thing as 3 plus 2. Same thing when you multiply. The associative property just says that you can group things together when adding or multiplying, and you can move the groupings around. It kind of connects right up with the commutative property. So it doesn't matter whether I add the first 2 together and then the third one, or I do the last 2 and then add the first one. You'll still get the same answer. The identity with addition just means that if you add 0, you get the same thing back. When you multiply by 1, you get the same thing back. So this is your additive identity is 1. Your multiplicative identity is your additive identity is 0. Your multiplicative identity is 1. And then if we take a look at the inverse, just means if you add the opposite, you get back to 0. Or if you multiply by the reciprocal, you get back then to 1. Okay? And then finally, the distributive property If you took A, distribute it, you multiply it in over any addition or over any subtraction, you'd get the same thing. You've used the distributive property before. That pretty much takes us through section 1, 2. It's the properties and their real numbers. Okay, so that's the first part. The second part is now 1, 3, and here's just some key vocabulary that I want to go through very quickly. So you're going to be taking a look. This is an example of an expression, and I wanted you to take a look at some different terms here. So if we take a look at the terms, I've got up here, an expression is just numbers, variables, or the product of a number and one or more variables. So there is no equal sign in an expression is the key idea. So how many different terms do we have up here? In this case, there's 1 term, 2 terms, 3 terms, okay? So a term, in this case, is separated by plus or minus signs. So in this case, we end up with 3 terms up above, okay? So that's the first part. We have 3 terms in this expression. Expression, it's not equal to 3 terms separated by 2 plus or minus signs. Then we talk about coefficients. So when it's a coefficient is really just the number in front of, at the very beginning, numerical factor of a term. So what are the coefficients in this one? The 4 would be your coefficient of x squared. The 3 would be the coefficient of y. And then -5 is just your constant, okay, because there is, and that's the next term. Are there any constants? Yes, there are, and that is -5 in this case. Okay. So you have 3 terms separated by plus or minus signs. The numbers in front of the variables are your coefficients, and -5 is your constant because there's no variable attached to it. So there's just some first part of some vocabulary. Second part, then if we keep going, if you talk about a product, if you remember, product is just another name for multiplication. That's all that's the difference there. So the example, what's the product of 5 and x? That would just be 5 times x, okay, or 5x. Or what if it was y times y? You could have y times y, or you could write that as y squared, okay? So that's all product is. It's just another name for multiplication. Quotient is just another name for division. So for example, when they say what's the quotient of 5 and x, that means 5 divided by x. Or what's the quotient of 5 and 15? That means 5 divided by 15, which we could reduce to 1/3. Okay? So that's your quotient. And then here's kind of one of the key ones, and we're talking about like terms. Remember, like terms have the exact same variables raised to the exact same powers. So what is an example of a like term to 4x? We could take 4x and I could add that to 3x because they both have x's in them, okay? So we could end up with a total then of 7x if I put those together. If we keep going, and I said, what about 7xy squared? So let's say I've got 7 of these xy squareds. I could add, let's say, 3 more, but to make them like terms, they'd have to also have xy squareds in them. So the coefficient tells you how many you have. And if I put that together, I'd get a total of 10 xy squareds. Okay? So that's the idea of like terms. You're adding the same variables with the same powers. And the coefficient is just telling you how many of each one that you have that you're putting together. So then if we go through and we start talking about, we're going to be using the order of operations to simplify. So just a reminder of what those are. Why do we have order of operations? It's a very simple reason. It's so that we all get the same answer. That's if you didn't have an order of operations, people could end up getting to multiple different answers. So these end up there so that you end up getting to the same answer. Okay, that's the reasoning behind it. All right, so then if we take a look, what are the proper order of operations? If you may have remembered from the past, if you remember PEMDAS, each one of these stands for something. The P you always do first are parentheses or grouping symbols, so it might be brackets, something like that. But parentheses are what you always do first. Then if we keep going, the E stands for exponents. We then would evaluate any exponents that we have, okay, any powers. Then the M and the D, those two go together, okay? M and the D combine, those stay together. And that is multiplication and division from left to right, just like you're reading a book. You just start going through and you do any multiplication as you work your way through, or division. They are either one. It does not mean multiplication comes first and then division. It means if division is the first thing in the problem, you do that first. And then the last thing, the A and the S go together as well. We add and subtract from left to right as well. Okay? And at that point, when you have an expression, once you've done those operations, you should be at the end and it should be completely simplified. Okay? And what we're going to look at today is simplifying expressions and then evaluating them is the second part. So let's get into simplifying expressions. First one, if we simplify an expression, that means we need to be able to put together our order of operations and properties. We're going to combine like terms. We're going to do any of the multiplying. We're going to do all of that kind of stuff. So let me give you an example here. If we take a look, let me keep this one down here. If I'm trying to simplify this expression, I need to go through and put any like terms together. So if we start taking a look, I've got 4 of these x squareds, and then I'm going to take away 6 of these x squareds. So if I put those two together, I would end up with 4x squared minus 6x squared. I get a negative 2x squared. Okay? Then if I take a look, I have a positive 1x and a negative 3x. Those two I can put together, and if I do, 1 minus 3 gives me a negative 2x. Now, the question a lot of people get to is, can I take these two and put them together? And the answer is no. And the reason is, this is an x squared, that's an x. We cannot combine x's with x squareds. Okay? So even though everything looks really similar, we have to leave that alone. And that is your simplified expression. That's as far as we can go. Okay? If I give you one more example here, and we're going to go through and take a look at this one. At this point, if I'm simplifying, we're going to add some things in. First step, I'm going to take care of this 5, and we're going to distribute that into the parentheses. So I end up with 5n squared plus 5n. Then I'm going to take this, don't forget the negative, we're going to take this negative 3 and distribute that. Negative 3 times n squared is negative 3n squared. And negative 3 times negative 2 is a positive 6n. Okay? Now we are basically right back to where we were in example number 1. Now we're looking for combining like terms. So once again, we take a look. Now I've got a 5n squared and a negative 3n squared. I can put those two together, end up with a 2n squared. Then if I take a look, I have a 5n and a 6n. I can put those together because they're both n's, and therefore I end up with plus 11n. And that is as far as we can simplify this algebraic expression. Okay? Again, we can't put those last two together because the first one are n squareds, and the second one, we only have n's in that case. Okay? So once we simplify, there's only one step left, and that is then to evaluate an expression once we've simplified it as far down as we can. So if we evaluate an expression, that means we're going to get an answer. Okay, we're going to plug something in. We're going to substitute something into that. And so if we take a look, we're going to take a look when x equals 1 in this case. We could have picked anything. But that means, let me get rid of this. That means if we're going to go through and we're going to plug in, let's say we've already done all of our simplifying and this is the answer we came up with. We can't simplify anymore, so now I'm ready to go through and evaluate when x equals 1. So if we take a look at that, that means I'm going to plug it in and get an answer. So we're going to do negative 3. When you substitute something in, make sure you put it in parentheses. Okay, we're going to square that. Minus 5 times 1 plus 7. And now we do our order of operations. So in this case, we would add, or we would do anything in parentheses, but there's only numbers in parentheses, so there's nothing to do there. So the next thing that we do is our exponent. We're going to square that 1. Well, in that case, again, it doesn't really do much. We square the 1, and we get negative 3 times 1, and we still have minus 5 times 1 plus 7. Now we move to multiplication or division. We just work our way through from left to right. Negative 3 times 1 is negative 3. Negative 5 times 1 is negative 5, and I still have the plus 7 at the end. And now we combine our like terms, basically. We add or subtract at this point. So negative 3 minus 5 gives me a negative 8. Negative 8 plus 7 gives me a negative 1. And there's our final answer. So when we plugged 1 in, when I'm evaluating when x equals 1, I got negative 1 out as an answer. So x equals 1, kind of my input. Negative 1 is the output. It's kind of like an x and a y, if you will. Let's do one more example here, even though I've got 2 listed. Let's do one more example. Let's do it when it's negative 2. So if I take that and I substitute that in, negative 3 times negative 2 squared minus 5 times negative 2 plus 7. The reason I wanted to do this one is it is really important, the parentheses, because if you plug this in, and we're now evaluating this exponent right here, negative 2 squared, if I plug that into my calculator and I plug it in this way, negative 2 squared, which a lot of students do, this is going to say, that the calculator is going to tell you that that's negative 4. And it is, because we're not actually squaring the negative in that case. We're only squaring the 2, and the negative is just coming along. What we want is we want negative 2 to be squared. That means it's negative 2 times negative 2, or a positive 4. That's why it's such an important piece, is to go through and actually take that and put those in parentheses. Okay? So in this case, we know that this part then over here equals 4. So I've got negative 3 times 4 now, minus 5, negative 2. So we've evaluated the exponents. Now we'll take care of the multiplication. So I'm going to put those two are multiplied. So I get a negative 12. These two are multiplied. So I get a positive 10. And then I still have a plus 7 at the end. Only thing left to do is put those together. Negative 12 plus 10 gives me a negative 2. Negative 2 plus 7 gives me a positive 5. And there's our final answer. Okay, so we evaluated that same expression, this negative 3x squared minus 5x plus 7, when x equaled negative 2. Okay? Again, it's kind of like we plugged in negative 2, we got out positive 5. It's like an ordered pair, your input and your output, x's and y's. Okay, that is the first 2 lessons, and I know it's a little bit long because we had to put 2 together, but your practice to learn for today then is it's a packet. It's worksheet 1, 2, and 1, 3. It's all together, and it's just a review of those sets of numbers from 1, 2, and then practicing some of the simplifying and the evaluating from section 1, 3. Okay, good luck with everything. I hope it goes okay, and we will see you in class then at some point.